Hey, math people, we're going to be looking at L'Hopital's rule today. Really should be called Bernoulli's rule, but we're going to unpack that a little later. It's the last little section here of my, what I'm calling contextual application of differentiation run through. It's Calc 1 still, differential calculus, but we're on our way. We're almost getting to Calc 2, almost. So what are we going to do? We're going to start with a warm-up. We'll define what are called indeterminate forms, and then we'll define the rule. We'll do a real soft verification of the formula, sort of a little hand wavy. We'll see the new rule with the old limits, and then we'll just grind out some practice and just remember some sort of cautionary tale of sorts. All right, this video is for you, Kevin. So what does that mean again? That means that you want to use the timestamps for you, pause, for you, and then be patient for you. Let's math. So evaluating the limits below. One of these you should just know how to do, just entirely just using limit rules, and then one of them you may have memorized from the limit chapter, and the other one's just like not doable. So you're gonna figure that one out for me. Yeah, we're throwing back to limits today. A little weird. All right, 3, 2, 1. So if you look at the first one, if you attempt to plug in 0, you get 0 over 0. Can't do that. So you can factorize the top, cancel out that whole, and then you end up getting 4. Within B, you may have been asked to memorize this from the limits chapter, and if you weren't, then you just don't know how to do it. And then C, you just don't know how to do it. So here's this thing. Each of these scenarios ran into 0 over 0, which is known as an indeterminate. So the indeterminates that you need to know for AP calculus are 0 over 0 and then infinity over infinity, although there are a few more or many more. Here are the ones that I at least know. 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, or infinity to the 0. Maybe there's more, but here's the list that I'm aware of at least. So yeah, the way that I like to sell these is that these are examples of not numbers, but like would have been, could have been, should have been numbers that are not sure of how to label themselves, I guess. They're trying to, so 0 over 0 is, it can't determine, it's indeterminate of whether or not it's 1, because it's trying to be like the same number over itself, or infinity, because it has divide by 0 in the base, or a 0, because it has 0 up top, and then 0 over any number is 0. So it can't really determine what it wants to be. Similar story can be made for infinity over infinity. Is it 1? Is it infinity? Is it 0 because you're dividing by infinity? Who knows? And then a similar story can be made for a lot of these other ones. But I like to think of it as it can't determine what it is. Indeterminate. Silly little approach to it. All right, so I don't know the whole lore to this, but here's what I do know, and maybe I'll correct myself in editing if I'm a little wrong to this. But from what I know, here's L'Hopital's rule. But here's the lore behind it. Bernoulli was a tutor to L'Hopital, and Bernoulli just showed him this right here, and L'Hopital's like, great, I'm gonna call it mine now. And then he just published it. I don't know if it was a hostile thing. If anything, maybe someone, I don't know, what are the odds that someone knows the history watching this, but I'm curious. That's the history that I know. So I don't like that it's called L'Hopital's rule. I guess it should be called Bernoulli's rule. Johann Bernoulli was his tutor. Anyway, here's the rule. If we have the limit of some like ratio of sorts of some function f of x over g of x, and it's approaching some a, then it's equal to the limit as of x approaches a of f prime over g prime instead of f over g if these conditions are all met, or not all met. One of these conditions are met. How about that? In conjunction with f and g being differentiable. So either the top and bottom limits must be 0, or the top and bottom limits must be some infinity, either negative infinity or positive infinity. So for the record, you can't mix and match. You can't have 0 and infinity and then use L'Hopital. It must be, when you compute it, so like looking at the warm-up, right? Each of these, we got 0 over 0. So that would all meet the criteria of 1 here. But if you would have gotten infinity over infinity, then I would have met the criteria for 2. Where f and g are differentiable. So bottom line is, if you do a direct substitution and you get 0 over 0, which was very common in the limits chapter, let's keep that in mind, or infinity over infinity, then you can utilize this rule where you just take the derivative of top and derivative of bottom. And then you take the limit from there. Here is like a super hand wavy, like big time hand wavy proof. I definitely make some generalizations with it, but I just wanted to show you something. I don't really like delivering something without some. There are many good proof, like actual proof videos, either graphical or algebraic on YouTube. But here's just a super small rundown with some generalizations made. Okay, so let's revisit the problems that we did in the warm-up, but this time we're going to use this new methodology. So I'd like for you to take the derivative of the top and derivative of bottom and then to compute the limit of that new expression, essentially. I'll show you what the official justification will look like for this right now. So 3, 2, 1. Here it is. So in order to say that we can use L'Hopital, so this is on the AP exam. What you would need to do is write everything that I wrote in this really obnoxious orange and yellow font here. You need to make a statement saying, okay, well, since the top limit is 0 and the bottom limit is 0, therefore L'Hopitals can be applied. And then you can apply it within the equality chain for solving the limit. I said is equal to, by L'Hopitals, I like to say LHOP up top, the limit as x approaches 2. I took derivative of top, it's just 2x. I took derivative of bottom, it's just 1. And hey, 2 times 2 is 4. Doing the same thing with sine of x here. Derivative of sine of x is cosine x. Derivative of x is 1. I can plug in that 0. I just get 1. So this was from that memorized expression, maybe from the limits unit, if your teacher made you memorize it. And then for this next one, I went ahead and what did I do? Oh wait, I could have done this one before, right? I don't know why I put question marks here. Why did I put question marks here? Why did I write Isn't this just the limit definition of the derivative e to the x evaluated at 1? Huh. Yeah, why did I write So anyway, the derivative of e to the x is e to the x, and you can just plug in 1. So this is just e. It's not it's e. Those are similar sounds, aren't they? Anyway, but the other way of solving it is by taking the derivative of top. This is a constant. It's just e to the x. And then derivative of bottom. Derivative of x is just 1. The 1 is the constant. So just plug in your 1 and you just get e. Okay. So I don't want to write that every time. I don't want to write this every single time. I've done it for years and I just don't like it. So here's how these are my house rules. This is how I did it in my university. I went to U of I as an undergrad, and they were fine with this. Let's all agree to just simplify it as we just write LHOP up top. So, here's just another example, I guess, of this limit. You could have done this problem, by the way, by this particular problem right here, using relative growth rates, like the log is slower than the quadratic. But, if you were to solve it using L'Hopital, I just write LHOP up top of the equal sign. And then to me, that's enough. You can't do this on the AP exam. That's not justification. But this is how I'm just cool with this. So I got 1 over x up top, I got 2x down below, and then I plugged in my infinity. So I have 1 over 2x squared, and 1 over big is just 0. So let's just do a few rounds of practice, right? Yeah. So I have 4 of these here. Some of these are limits that do not require L'Hopital. In fact, you shouldn't use L'Hopital on. You can only, in this house rule scenario, I'm only going to give 0 over 0 and infinity over infinity, right? So if you don't get those results with the direct substitution, do something else. Don't do L'Hopital. So I'm going to give you some time to do these 4. Give them a go. 3, 2, 1. Okay. So the first one, you should have used L'Hopital, or you could use relative growth rates, right? You can say e to the x grows faster than x, therefore runs to infinity. If you don't like that, you can say by L'Hopital, this would be e to the x over 1, and that's just equal to infinity. Limit doesn't exist. This looks like an infinity sign, but sideways. But it's an 8 and not a sideways infinity. So if you plug in 8, please do not L'Hopital this. This is just 8 over e to the 8. You cannot L'Hopital that. That is a direct substitution and continuous at 8. All right, with 3, I could have used, could I have used limit definition of a derivative? I think so. But I didn't. We just ended up using L'Hopital within this one because if you do plug in that 25, you get 0 up top. If you plug in a 25 down below, you get 0 down below. And I just took the derivative right away. So I took the derivative of this expression, lowered that x square, x to the 1/2 down to the denominator, and I plugged in that 25. It should be 1 over 10. Within this one, this is a L'Hopital because the natural log of 1 is none. And then down below, 1 squared plus 4 minus 5 is 0. So you get 0 over 0. So this simplifies to 4 over x. And then over 2x plus 4. You can directly sub in that 1 at this point to get 4 over 6 or 2/3. So you should not have L'Hopital 2. The other ones were all 0 over 0 L'Hopital cases. Oh, wait. 1 was an infinity over infinity L'Hopital. And then 3 and 4 were 0 over 0 L'Hopital cases. Yeah, there's like an overabundance of memes on L'Hopital for no reason at all. So I'm just going to show a few of them. All right, within 5 through 8, give these a go. So be on the lookout for L'Hopital. 3, 2, 1. It looks like you should have L-hopped 3 of these as well. 5 was perfectly fine to L'Hopital. You could have done the normal factor cancel thing. But look, we have a new rule now. So I got 0 over 0. I just used L-hop, and then I plugged in my -4, and I got -1 over 3. Within 6, not L'Hopital. This is not L'Hopital. You can just directly sub in this 0, and the cosine of 0 is 1. E to the 0 is 1. So since that negative's lurking up front, I'm getting -1 as the solution. Within 7, I'm seeing here that I have sine of 4x over sine of 2x. I can L'Hopital this, right, because you get 0 over 0. So I get 4 cosine 4x over 2 cosine 2x. If I plug in that 0 again, these are both just 1, so 4 over 2 is just 2. This was definitely L'Hopitalable. This was a 0 over 0, 5. 7 was a 0 over 0. And then 8 here, which again looks like that infinity. Whoa. Limit as x approaches infinity for this expression. Again, another L'Hopital. You didn't have to use L'Hopital, though. You could have done either relative growth rate. You know the cubic grows faster than the cubic root. Or you could have just simplified the expression. You know that this is x to the 1/3 and this is x to the 3rd. So you could have just done exponential simplification there. Either way, so I did L'Hopital, obviously, for L'Hopital practice. And I got this expression bringing that -2/3 down below. We would make that x raised to the 8/3. And then you can plug in that infinity. 1 over big is just 0. Woo! All right. Yeah, this is what happened in real time. Okay. And then last 2 of this round practice through L'Hopital. So if I am approaching 0, for this expression, let me know how that goes, and here I'm approaching infinity. So 3, 2, 1. 2 different L'Hopitals. Did have to use L'Hopital in both. Here's the fun part, though. Within 9, you had to do L'Hopital twice. Because look, if you take that first derivative, you get 6x up top. And you take that first derivative down below, you get 3 sine 3x. So when you plug in that 0, we're getting 0 over 0 again, right? We get 0 up top, sine of 0 is just 0. So you are allowed to use L'Hopital as many times as you want, so long as you continue to get those indeterminate values, right? So I got 0 over 0 after the first L'Hopital. I got 0 over 0. Well, wait. I got 0 over 0 without L'Hopital, and then I got 0 over 0 within the first L'Hopital. And then after that, I plugged in 0 again. I'm just getting a cosine of 0, which is a 1. So 6 over 9 is 2/3. So it ended up working after 2 L'Hopitals. But be careful. Sometimes if you L'Hopital once and then you get 1 over 0 after, that's then undefined. Or the limit does not exist. So you can't use L'Hopital in those scenarios. You can't use L'Hopital for does not exist scenarios. It's only for the indeterminate scenarios, 0 over 0 or infinity over infinity. So last one here, 10. I brought the 4 up front just by using a log property. Made my life a little easier. But still, I plugged in those infinities, and then same thing with the 3. I brought that up front. So I have infinity over infinity. That's no good. So I did L'Hopital's, derivative of top, derivative of bottom, and then I plugged in those infinities. No, I didn't do that because then I would have 4 over infinity and then 3 over infinity, which is 0 over 0 again. I did algebraic manipulation for this step, from this step to this step. I just brought this x up top and this x minus 1 down below. So that's same powers of x. This is like a horizontal asymptote. So as you approach infinity, you get 4 times big over 3 times big, and those bigs just cancel to get 4 over 3. All right, so hopefully you're feeling like this. Who knows? All right, and let's just make sure you're good on one last little difference before we go here today. These are two different things. These are two different things. If you write limit as x approaches 0 in front of an expression, that's different from the derivative is equal to 0. What? It's different from d dx, and it's also different from the derivative equal to 0. Anyway, see if you can just see the difference between these two. Just trust, 3, 2, 1. Because guess what a lot of students do? They start to think that this is just the new quotient rule, which is not true. So if you apply L'Hopital within this expression, you should get -1/2. But if you just find the derivative of this expression, that requires quotient rule. So you cannot just L'Hopital everything. People get what I call L'Hopital happy. They start to apply it to just any fraction they want. That is so totally not the point of this. It is a useful tool, do not get me wrong, but it is in the explicit scenarios where you're getting 0 over 0 or an infinity over infinity, right? So just be on the lookout for these. They occur quite often in calc. And that's what I'm going to say Bernoulli helped us out with here. Let's call it that. Bernoulli. Thanks, Bernoulli. Math on.